The infiltration assignment that you've got is due on Monday of next week, and I've finished grading the first homework assignment. I graded that yesterday afternoon, so everybody should have a score on that. I'll be leaving comments in the Blackboard that, like, when points are deducted, it'll explain what it was taken off for, and in some cases I'm offering suggestions like, anytime you use Excel on your homework assignment, I'm going to ask you to submit your spreadsheet just so that if I have questions on what you've done, it'll allow me to get into the details. So please be sure and take a look at the suggestions. There are a couple of students, for example, whose their scan quality on the PDF wasn't quite sharp enough, and I had some suggestions on how that could be improved. I'll try and do homework 2 this afternoon and tomorrow so that I don't fall behind on the homeworks. But so homework 3 is due on Monday, and part of it is solving the Green-Ampt equation, which we're going to do the example today for that. Just to refresh your memory on what we talked about in class last time. So in class on Monday, that's when we watched that video, right? Yeah. So the majority of that was talking about how water moves through the soil. And what we're trying to model with the Green-Ampt equation, which we're talking about today, is the rate of infiltration. So these two curves illustrate what's called the potential rate of infiltration, and what you'll see is that it's declining during a storm. So this top curve here is the rate, lowercase f, and capital F is the cumulative amount of infiltration. So it's the depth of precipitation that has penetrated into the soil. And it's always increasing. The depth is not declining. What's declining is the rate. And based on what we talked about in class on Monday, who's willing to guess, or maybe I said it already, why is it the infiltration rate's decreasing as a storm goes on? At the beginning of the storm, the rate of water infiltrating into the soil is high, but then it goes down over time.
Is it because the ground already moist after can't go no more water?
That's right, that the ground is becoming more moist. That's a part of it. And even before we hit saturation, the rate of infiltration is declining. So it's not just because of saturation, although when the pores are fully saturated, then that does dramatically decrease infiltration as well. But the infiltration rate declines before the soil is saturated. So there's more to it than saturation. What's the other thing? Why does water infiltrate? What are the two main forces that draws water into the soil? Oh, we should have had a quiz today. That would have been so much fun.
So I mean the pressure that draws the soil in.
Okay, good. There's the suction pressure that's decreasing. And why is it decreasing? You're right. Why is the suction pressure decreasing as water is entering the soil? Well, it's that suction pressure, the table of data that we saw here is for dry soil. So the wetting front soil suction head, when the soil is dry, there is cohesive and adhesive forces that cause the water want to bond with itself and bond with other surfaces. And so in the case of capillary effect, it was the cohesive forces with water being attracted to itself and the adhesive forces of water being attracted to the other materials like the glass plate. Or in the case of soil grains, water is attracted to the surface of the soil grain. But as water goes into the soil, then that driving force decreases, and all that's left is the secondary effect, which is gravity. So the two main forces that causes water to infiltrate into soil is gravitational forces and then the soil suction head. So as the water becomes moist, the soil suction head decreases. And so there's this declining rate. the declining rate of infiltration. So this is the Green-Ampt equation. We can write the Green-Ampt equation in terms of calculating the cumulative infiltration depth from time 0 to some time in question. Let's call it time t. And that's what's written here. And if you look at what is the infiltration rate dependent on, it's dependent on hydraulic conductivity. That's part of it. But there's also the soil suction term. So the two main terms here kind of relate to the two forces that drives water into the soil. There's the gravitational effect, and then there's the cohesion, adhesion that's related to soil suction. So this takes into account the gravitational effect. The second term is taking into account the cohesion and adhesion that drives soil being drawn in by water being drawn into the soil through suction. What makes it complicated is that the cumulative infiltration depth is both the thing that we're trying to calculate, and also it influences how much of the suction head effect takes into account at any given time. So the more rainfall that has been infiltrated, the less the suction effect is going to be. So it's on both sides of the equation, and so we have to solve this equation starting with the guess, and then we're looking for the left-hand side of the equation, the right-hand side of the equation, and we're looking at what is the value of certain parameters that makes the left-hand and right-hand side of the equation equal to each other. Like, what's the guess value for the infiltration depth that makes this equation equal? So we can also write the Green-Ampt equation in terms of, at any given time, what's the infiltration rate. So lowercase f would have units of centimeters per hour, whereas capital F would just be units of centimeters. So it would mean how many centimeters of precipitation had infiltrated from the beginning of a storm up to time t. When we talk about amount of rainfall as a depth, if you wanted to turn that into a volume, you multiply that depth over the area that the rainfall has fallen onto. Some of the other terms in here are soil characteristic terms, like, for example, suction head. We've looked at a table that compares the suction head of sand to the suction head of clay. And so the clay suction head, remember, was relatively high because the small diameter voids means that there's lots of surface area for the water to be in contact with, whereas in the case of sand, the suction head is relatively low because the specific surface area of a sand grain, meaning the area relative to the volume of a sand grain, is much lower than the case of a small diameter particle like a clay particle, where it has a lot of surface area relative to its volume of each individual particle. So one of the terms is the suction head. Delta theta, the increase in soil moisture that occurs during infiltration. And in the Green-Ampt simplification, if we go back to like the visual representation of it, what we're assuming is that the water goes from initial moisture content and instantaneously it becomes fully saturated. That the wetting front moves through the soil as a binary wave, rather than, in reality, we know that it's a more gradual progression that's related to the distribution of void diameters. But in this model, the simplification is just saying that it's fully saturated up to a certain depth. And so in this Green-Ampt model, what we're going to use as one of the parameters here, the delta theta, is just how much increase in moisture content there is between the initial moisture content and being fully saturated. Okay, one of the things to point out is that the delta theta, the way that we estimate that, how much extra moisture there is we're just saying that it's the effective saturation is some of the voids aren't interconnected. And so not all of the voids in soil are actually useful for transmitting water. Some of the voids may be completely isolated and there's no channel in or out of the void. And so it's, we could talk about the porosity of the soil, but its effective porosity would be lower if it has voids that aren't connected. But the water can actually only fill up the voids that are interconnected. And so there's this differentiation between the saturation and the effective saturation. So S sub E is a parameter that will be given to you in a problem statement. That's how much of the saturation is effective, taking into account the voids that aren't connected. And effective porosity also is part of calculating the increase in moisture content. So in the example that we're going to work just in a minute, we're going to start off with knowing the hydraulic conductivity of the soil. So K is just a physical constant. It's length per time for a soil, and that'll tell us how quickly the water could penetrate through due to the effect of gravity. We'll know from time 0 up to a given time in question. So T will be the increment that we're interested in. We'll also have to know the soil suction head, which is another property that would be either determined in the lab or estimated in the field given a table of soil properties. And then how much moisture increases during the infiltration, meaning what was its initial saturation percentage versus when it's fully saturated. So we'll just have to start with a guess value of the infiltration depth, and as a starting point we can directly calculate the hydraulic conductivity times T, because that doesn't have this F sub T term. So just as a starting point, sometimes we'll, as our first guess, use the hydraulic conductivity multiplied by the time increment, and then from there use not goal-seek, but we're going to use solver, because goal-seek is useful for a lot of applications where there isn't a really tight precision that has to be achieved before it stops iterating. But I've noticed in some past example problems that Green-Ampt equation, Excel will give up too early when it's using goal-seek. And so solver, you can specify how much precision you want for it to consider the solution converged. And so I'll show you in a minute how you can turn solver on in your computer. So we'll go through this method, and we're going to use some of the soil properties that are taken from this table. This is a table in your textbook. It's also in the notes. But what we're going to do is we're going to, for the soil in question, just see how does the infiltration rate decline over time as the storm moves on, as the soil becomes saturated, as the suction head decreases. How does the infiltration rate go down, and then what does that mean for the cumulative infiltration rate? So here's that example. This is a silty clay soil. So the effective porosity, the soil suction head, and hydraulic conductivity, these are values that would be characteristic of silty clay. And what we want to know is if there's continuous ponding, and by the way, that's one of the assumptions that's built into the Green-Ampt equation, is at time 0, the Green-Ampt equation says we, just for simplification's sake, have to assume that there's been sufficient water at the surface the whole time to be pushing the water down through the soil. So think about what you've learned in the prior homework assignment about precipitation properties. Like in a type 2 storm, the precipitation intensity is pretty low at first, and it's not until that midpoint of the storm when the intensity is really high and then it tapers off again. So this Green-Ampt equation requires us to assume that there's been so much water at the surface that the precipitation exceeds the infiltration rate initially. Sometimes that'll be true, sometimes it's not true. But we have to know that if there isn't continuous ponding, like if the precipitation rate is less than the infiltration rate, then the declining rate of infiltration will decline less rapidly than it would under Green-Ampt. So this is, Green-Ampt is going to give us kind of, you could think of it, the worst case scenario for what's the quickest that the infiltration rate could decline if there was continuous ponding. And if there's not continuous ponding at the surface, then the infiltration rate won't decline as quickly as is predicted by Green-Ampt. All right, so now with that caveat, we're going to find out what's the infiltration depth at 0.1 hours and 0.2 hours, assuming effective saturation of 45% and continuous ponding. All right, so the template file that I put online is this Green-Ampt method example / student start. It's a pretty simple template. It's just got a spot for us to put the values into these defined terms. Oh, it's this first one. Okay. So the problem statement says that based on the soil characteristics, for a silty clay soil, let's use this midpoint value for the effective porosity. So here, this column, effective porosity, what is this one? Silty clay. So we went to silty clay, and 0.423 is what we'll use for the effective porosity, 0.423. Suction head, the problem statement says for this silty clay, let's use 29.22 centimeters for the suction head. And then the hydraulic conductivity for this soil, expressed as centimeters per hour, is 0.05 centimeters per hour. Okay. The effective saturation of 45%, we have to express it as a decimal here because of the way that we're going to calculate the delta theta. So for 45%, we just put in 0.45 for the effective saturation. And now we'll calculate the delta theta. So this is how much the moisture content increases. So there was a certain amount of moisture to begin with. And so when you go from the starting moisture, which is this effective saturation is telling you before the storm happened how much water was in there. And then delta theta tells you how much additional water can be can go up, and it's like expressed as a fraction. So the formula here is 1 minus the effective saturation minus multiplied by the effective porosity, 0.232. So that means, like, if you have a 1 square centimeter of soil, you know, soil is a mixture of 3 things. It is the grains, so it's the solid material, it's the voids, the empty space between the grains, and then some water coating the soil grains. So what this is telling us is if this is 1 centimeter by 1 centimeter by 1 centimeter, that 23% of that is going to be increased water from the beginning of the storm to the end of the storm. So, like, if we think about it as a depth, if we have 1 centimeter of water that penetrates, it's going to have to penetrate more than 1 centimeter vertically down, because some of the space that's below the surface already was water, some of it is soil grains, only 23.2% of it is voids. And so if we had 1 centimeter at the surface, like, how deeply will it penetrate? We would do 1 divided by 0.23. So it would penetrate 0.23 to penetrate down about 4.3 centimeters. So if it's a freestanding 1 centimeter surface of nothing but water and it goes down into the soil, it's going to penetrate further. Okay, so we want to know how much is the infiltration depth after 0.1 hour. Okay, so T is 0.1. We want to know how much water infiltrated at 0.1 hour. And the simplification, maybe the starting point guess, is K times T. So just as an initial guess, K times T would be 0.005. Now, I've got a formula in there right now, and I want it to be a number. So I've calculated this 0.005, but I'm going to delete that. I'm just going to type in the number, 0.005. Because if it was an equation, I wouldn't be able to do goal, seek, or solver. I have to have a number in there to be able to use solver later on. By the way, speaking of solver, let me show you now how to turn that on. If you go to File, and then down at the bottom is the Options. It's an add-in that we want to enable. So among the Excel options, you'll see on the left-hand side here is a bunch of different Excel options. Click on Add-ins, and then we want to manage the add-ins. So I'm going to click on Go, and you can see this computer already has the solver add-in enabled. Unless you've turned it on before, yours won't be checked. So you check it and then click OK. The only negative thing is that it takes Excel a little bit more time to load when you have the solver add-in enabled, like 4 times longer for some reason. I don't know why. So usually on my computer upstairs, Excel turns on in about half a second if solver's not enabled, and it takes 2 seconds if it is. So I mean, that's no great inconvenience. But when you've enabled it, what you'll notice is that on the if you go to the Data tab, then over here under Analyze it says Solver, and that wouldn't be there if you don't enable that as an add-in. So we're going to need access to that when we do our calculations. So that's the infiltration depth guess. We've just started with a guess, and now we're going to use this equation here to calculate what I'm calling RHS. That means the right-hand side of this equation. Okay, so it is K times T plus the suction head multiplied by, and I guess, you know, since I'm going to want to drag this down to the next row, maybe I should anchor any references up to these constants at the top. So I'm going to press F4 for any of the references up at the top. So where did I leave off? I've got K times T plus the suction head multiplied by delta theta multiplied by the logarithm of 1 plus. Now I've got f sub t, and so I'm going to have to refer to my guess value, which is in B10. I can't click on the location because this equation is centered and it's in the wrong, like the equation itself is on top of the cell I want to click on. So that's why I've just typed in the value there. So 1 plus f sub t divided by soil suction head, anchor that reference, times the delta theta, and anchor that reference. And so let me just make sure I need to anchor this one. Okay, so I've typed in the equation for the right-hand side of the equation, and the two are not equal. If we want to calculate the difference, one minus the other, the fact that they're not equal tells me that my guess was wrong. And it looks like maybe the guess is too small, right? So what if I say 0.006? 0.007. See how small the difference is? If we just did goal seek, I think it would quit too soon. Now maybe it won't in this particular case, but like as a more general tool, let's just give it a try. Goal seek. So what we want is we want the difference to be 0 by changing that one. Okay, that's a pretty good solution, but you'll notice that the difference isn't actually 0. It stopped iterating too soon, and so if we use solver, Here in the options for solver, you can tell it the precision constraint. So you could tell it how close the two things have to be for it to stop calculating. So right now you'll see the precision, there's more digits there, like GoalSeek quit a lot more quickly than solver will, and I could add a few more zeros if I want it to be really precise. Okay, so I want it to say our objective is this to a value of 0 by changing the guess. So 257 isn't really the answer. If I tell it to solve and it goes all the way, see how it says 264? So it quit too early before. It looked like the two was equal, but they weren't. And so that's why we use solver for the Green-Ampt equation and not GoalSeek. If we had just said, well, 0.257 is equal to 0.257, it wasn't looking at enough digits of precision. Like, we want it to be exactly the same. Like, if we show all of these decimals, we want it to be really, really the same, because it's not until it is the same across a lot of digits that the two truly match. So we don't have to necessarily see all those digits, but hopefully you see the point about solver versus GoalSeek. Okay, so what this means is if we had this soil and we kept putting water on it, that means keep putting water on it means that it's continuously ponding at the surface. Then after 0.1 hours, that would be 6 minutes. After 6 minutes, we would have had 0.264 centimeters of water infiltrate. That doesn't mean that's how far the water has penetrated. That means that's the amount of water. And so when this says infiltration depth, I suppose that's kind of a misnomer. To be more precise, we could say depth of water that has infiltrated. Because how far has it infiltrated? To know the infiltration distance, we'd have to divide this depth by 0.232, and then that would tell us the infiltration distance. So this is just telling us an amount of water. 0.264 centimeters of water for this particular soil. That's how much water would infiltrate in 6 minutes. Now, if we calculate infiltration rate, we're going to calculate the rate at a given instant of time. So if I calculate lowercase f of t, that's telling me exactly at 6 minutes after this experiment starts, what's the infiltration now. So it's not the average rate across the period from 0 to 0.1. It's the infiltration rate just at a single moment, at the moment in time of 0.1 hours. So now let me use this equation to calculate the infiltration rate at this particular moment in time. It is K times suction head times delta theta divided by f of t plus 1. So at 6 minutes after the storm starts, then right now the infiltration rate is 1.34 centimeters per hour. But it's going to be going down. And that's the purpose of looking at this at two different times, at 0.1 hour and at 0.2 hour. So now what I hope this shows us is that the infiltration rate is slowing down, that it's following this model of declining rate of infiltration. Because what we know, the physical reality, is that the suction head decreases as the water begins to saturate the soil. We saw that in the videos, that the wetting front is moving quickly at first, but then the more saturated the column of soil gets, the wetting front is slowing down because there's less of the driving force drawing it into the soil. So now let's do the same thing with 0.2. We have to have some guess and the good starting point would be K times T. So K times T is a fair starting point, 0.01. All right, now I can't leave the equation in there, otherwise goal-seek won't work later on. So I'll just type 0.01. So that's a number rather than a formula. Right-hand side, if I want, I could just drag the equation down because I anchored all the references. I'll do that. You don't need to see me type an equation in again. This is the equation I'm dragging down here. Okay, so the two are not equal. The left-hand side of the equation minus the right-hand side of the equation. It seems like it's pretty close, and again, we'll see that goal-seek doesn't do good enough. Poor goal-seek. Not getting any love today. So we want that to be equal to 0 by changing that. It looks pretty close, 0.366, 0.367. It does what it can, but it's not enough in this case. If we use solver, which remember in solver, we can tell it exactly how much precision we demand to see. It's probably good enough. Our objective is for the difference to be 0 by changing the guess. It solves, it says 0.375. So that's right. Before it was saying 0.367. So this is the cumulative infiltration depth after 12 minutes. So think about how much water penetrated during the first 6 minutes and then compare it to the next 6 minutes. You can tell that the infiltration rate is going down because in the first 6 minutes it was 0.264 centimeters. And if it was staying constant, then after 12 minutes, it would just be double that. But it's less than double, right? It looks like it's maybe 1.5 times as much, or maybe even less than that. The infiltration rate is declining. And maybe the most vivid way of seeing that is with lowercase f of t, the infiltration rate. Let me just make sure that I anchored all the references up here to the constants. It looks like I did. So I'll drag this down, and the infiltration rate after 12 minutes, 0.2 hours, is now just 0.96 centimeters per hour. We will do some watershed models with like industry software packages, and it'll handle all this in the background. But you need to know the theory of how the Green-Ampt equation works so that if what the computer model does is nonsensical, you're able to determine if something's a realistic calculation. You need to be able to do a reasonableness check. You know, like, is what the computer gives you realistic given the situation? And the other reason why we're kind of doing this manually is it's really important to know the assumption of continuous ponding. Green-Ampt equation only works if there's ponding at the surface from the beginning of the storm. So what that means is that the infiltration, that the rainfall rate has to be higher than the infiltration rate at the beginning. So, like, what was the initial infiltration rate? So we could find out what was the initial infiltration rate like at the very beginning of the storm. So instead of at 0.1 hours, what about 0.01 hours? So that's even before 1 minute has occurred. So if we run the solver again at 0.01 hours, where we want the difference to be 0 by changing that. So at the very beginning of the storm, it was infiltrating at 4.16 centimeters per hour. So you have to know, like, what was your rainfall pattern? How intense was the storm at the very beginning? Was it more than 4.16 centimeters per hour? If yes, then continuous ponding is a valid assumption. If no, then continuous ponding is not a valid assumption, and it'll actually, the infiltration rate will decline less quickly than is predicted here. So does anybody have any questions both about the theory or about the application in the spreadsheet? The book explains all this lots better than me. I hope you'll read it. All right. So let's talk a little bit more about ponding. What I mean by ponding, we could call it puddling or pooling at the surface or like saturation at the surface. This is what my yard looks like right now because, we had all that snow and then it got warm quickly and it's supposed to rain, I think, starting tomorrow. My guess is that there could be some flooding. Whenever you have a lot of snowfall that warms quickly and then it rains as well, that's just a recipe for disaster and flooding because the soil is saturated and then you put extra water on top of it, it's just got nowhere to go. So this is ponding. And we can calculate how long it takes for ponding to occur if the precipitation rate is less than the infiltration rate. That's going to be most of the time. It has to be a pretty big storm. Like what we just solved here for 4.16 centimeters per hour. What is that in inches per hour? Inches per hour. There's 2.54 centimeters per inch, right? Divided by 2.54. So 1.64 inches per hour. In Huntington, let's see what kind of a storm are we talking to get that amount of precipitation. Here in West Virginia, for us to get 1.6 inches per hour as the intensity, let me switch it from precipitation depth to precipitation intensity, drag this over to the tri-state area, and then look down here. What kind of an intensity is 1.6 inches per hour? So a 1-year storm, we'd see it for a storm duration of 30 minutes. So you'd see it once a year for a storm that lasts 30 minutes. But it's not going to be the storm that comes multiple times per year. It's maybe like a 1-year storm. So continuous ponding for the big one will be a valid assumption, but there will not be continuous ponding for most of the little storms during a year. So how do we calculate how long does it take for ponding to start? Because the infiltration rate is going down. We've seen this curve already, the declining potential infiltration rate curve. And if the rainfall rate is constant, there's a certain point where these two curves intersect, where the potential infiltration rate is declining and the rainfall rate finally is greater than the infiltration rate and ponding occurs. So we could calculate the worst case time to ponding with this method, but what this approach that we're going to use, it kind of oversimplifies because the infiltration rate curve isn't going to be declining that quickly if it's not fully saturated. So it's like we can't get away from these simplifications. This is going to be like the worst case ponding time. So ponding won't happen any sooner than what we're going to calculate. What we're doing is, in this case, looking at the cumulative infiltration curve and looking for the point of intersection between the rainfall curve, the cumulative rainfall curve, and the cumulative infiltration curve. Because where the two intersect, that means that there has been finally enough rainfall to fully saturate the soil voids. And so anything beyond that is going to be excess water that starts to flow over the surface. So remember, we care about infiltration because we want to know how long is it going to take for water to start moving off the soil and towards the outlet, like towards the grates or causing flooding. Now, how much rainfall is there going to be before there starts to be runoff? We want to be able to predict runoff. And this is telling us time to ponding is an important part of the runoff time, from when a storm begins to where you start to see water at the outlet. So here's a way to calculate the runoff time that we can use the rainfall intensity, the hydraulic conductivity, the suction head, and just calculate it directly. So in this ponding time example, we've used the same soil characteristics. We have the same initial effective saturation. What if the rainfall intensity was 1.5 centimeters per hour? Could we calculate how long until ponding occurs? So in the template that I gave you, there's a second page there that allows us to calculate the time to ponding here. And we want to calculate how long until the ponding occurs. Let's fill this in with the effective porosity, which we already knew was 0.423. The suction head was 29.22. The K value, the hydraulic conductivity of the soil, is 0.05 centimeters per hour. The effective saturation is 0.45, and then the delta theta we could calculate in the previous step. It was 0.232. So 0.232. We have to start off with a guess for how long it takes, because we don't necessarily know the time to ponding until we know the rainfall intensity rate at a certain level. So in this example, we're saying, what if the rainfall intensity is 1.5 centimeters per hour? How long is it until the ponding occurs for that? So the right-hand side, if we just start with a time from 0.15 hours, 0.156 hours was, I guess that's going to be my my final answer here. Cumulative infiltration was there from time 0 to 0.156 hours. Oh, that's something I want to ask later on. Okay, let's start with a guess of just 0.1 hours. If we have the infiltration depth guess of 0.05, which is the 0.005, the K value multiplied by the time, the right-hand side equation of the F sub t equation. So have to type this in again. It is the K times T plus theta times delta theta times logarithm of 1 plus F of t, the guess, divided by suction head times delta theta. Okay, and we look for the difference. We want, oh, I have to do the equation. It's this minus that. Okay. So we want the objective D17 to be 0 by changing the guess. Okay, so the two aren't equal. If we have a storm intensity of 1.5 centimeters per hour, then the time to ponding, T sub P, is the K value 0.05 centimeters, the suction head 29.22 centimeters, the delta theta is 0.232. Okay. The rainfall intensity, if the storm is 1.5 centimeters per hour, so 1.5 centimeters per hour, and then we multiply that by 1.5 centimeters per hour minus the hydraulic conductivity of 0.05 cm per hour. Okay, so if you've got a calculator handy, let's check to see what is this going to be. It is 0.05 times 29.22 times 0.232, and then 1.5, 0.05. Okay, 0.156 hours. And so what we'll see is we can pick a time, like if we know from this equation that the time to ponding is 0.156 hours, assuming continuous ponding, then we could find out like what is the infiltration depth that intersects with that. So we run this again, 0.33 centimeters. So think about this curve where we said a certain infiltration depth and a certain time that coincide with the rainfall curve and the infiltration curve together. So if you look at the next homework assignment, you're asked to use the Green-Ampt equation, and so you can use this same approach. Let me know if you have any trouble getting Solver enabled on your Excel. I can help you with that if you need assistance for it. But we'll talk more about ponding and estimating infiltration rate in our class on Friday. There is a simpler method than Green-Ampt, but it doesn't have as much flexibility. It's not quite as accurate. So we'll talk about that on Friday.